Hello, my name is Nick Atkins, and I'm a senior physics major at Gustavus Adolphus College. My project is on hydrocarbon seeps, with emphasis on locating, quantifying, and predicting oil slicks in the Santa Barbara Channel. First, let me show you my final image showing the three main oil slicks in the Santa Barbara Channel. Now, in order to understand how this image came to pass, let me take you through my methodology and initial plan over the last few weeks. First, a little background information. Santa Barbara is known for its notorious oil slicks. These hydrocarbon seeps sometimes spew oil. Thus, this oil is both detrimental to the environment and to boats, and represents a clear and persistent problem in the Santa Barbara Channel. Now, in order to, thus comes my objectives. First, I wish to locate the oil slicks in the Santa Barbara Channel using the master imagery. Second, I want to quantify the area of those oil slicks in the Santa Barbara Channel. And third, I want to predict where those oil slicks are going to go. In order to accomplish this, I look first to a Casello et al. 2010 article, which used thermal infrared imagery in order to see the different temperature signatures between the cooler water and the warmer oil. I also looked to a Hugh et al. 2009 article, which used transit lines in order to show the different reflectance between the sea surface and the water. This shows my initial plan using the transit lines drawn across a ship path, as highlighted by the black line. As you can see, there is a clear drop in pixel value across the ship path, shown here by the white lines. Thus, using this methodology, I can see decreases in pixel value, or increases if I wish. A problem arises here, and that is, how do I possibly quantify this information? In order to accomplish this, I quickly learned and wrote a MATLAB script, which took in an oil transit line information and then gave me the location of any possible oil slicks along that line, along with the average value of the oil slicks along the line, while also giving me a confidence percentage, giving me an idea of how confident was I that that was actually in fact oil. This program also acted as a filter, requiring at least 2 points in quick succession in order to begin triggering and counting the region as an oil slick. Thus, I wanted to apply this to my actual master imagery, which came in a few weeks later, as seen here. This is band 47, a thermal band, showing flight tracks 10, 11, and 12. As you can see, there's a dynamic shift in contrast in this image, but there's no clear oil, at least none that I expect compared to, say, this Aster image of the deep horizon blowout taken May 1st. As you can see, there's a very clear contrast between the oil and the sea surface temperature. Thus, I have to ask myself, what is my image showing? Naturally, being a thermal image, it's probably going to be showing the sea surface temperature. In order to prove this, in order to confirm this, I look at the MODIS, Sea Surface Satellite Temperature data, taken June 30th, courtesy of Miss Snow. Now, in order to compare these images properly, I first grayscaled this MODIS image, and then I superimposed the master imagery on top of it, as seen here. As you can see, there's a pretty clear correlation between the two. In order to see even a clearer correlation, I put the transparency at 53%, allowing to see the contrast between the two images, as shown here. As you can see also in this image, there is clear upwelling, or what I would suppose to be upwelling, shown in the bottom left-hand side of the image, where the two images both exhibit a darker, cooler color. Nevertheless, besides this image being really, really cool, to say the least, I'm still left oilless and need to find a new approach on locating oil in the Santa Barbara Channel. So naturally, I look first to the visible spectrum. As oil is visible to the human eye, maybe it'll also be visible in master's human eye, or master's visible imagery. As you can see, this is a true color image of the Santa Barbara Channel, showing flight path track number 11. As you can see, oil is clearly visible. Thus, I decided to run with this idea and see if I could quantify the area of the oil slicks using the true color imagery. But I ran into a problem, which is the cross-track illumination problem. Now, this is essentially that the side values of the pixels blow up in value, in that the image sides become almost unusable. You can't really differentiate if any image is there in the sides. Nevertheless, luckily my oil slick happens to be, for the most part, by and large, in the middle of the image. Thus, I avoid this problem, but still represents a problem if I want to locate oil near the shore. Thus, in order to correct this, I tried using a cross-track illumination correction, along with MNF, along with a PCA as well, having not any real luck with it. Though that past image I just showed you actually is cross-track illumination corrected, but it represents more of an aesthetic fix, rather than an actual clear fix in the image, as the values on the ends still blow up. This problem was a lot larger than I guess I was able to deal with, and represents a clear potential future in order to try to find out how to fix this issue. Nevertheless, I persevered forward, using an ROI established over the center region of the image. Now you may ask, why do you need an ROI over the center of the image? Well, there are two reasons for this. First, it gives me a mean, and second, it gives me a standard deviation. Now, any pixel value above the mean means it's going to be a brighter pixel, which is going to correlate to oil, because oil is going to appear more reflective on the surface of the water, thus appearing as a brighter pixel. Also, using the standard deviations, I can establish different levels of oil density. As a pixel at the first standard deviation is going to be less reflective than one that is at the third standard deviation. Therefore, a third standard deviation pixel should correlate to a higher density oil area. Thus, I ran with this idea and applied it first to the middle oil region, as seen here. Zooming in on this middle oil region, I established an ROI over this region in order to rid any excess noise and get rid of the cross-track illumination problem, or at least try to mitigate it. As you can see, this image was rotated 90 degrees, and you can see that there is the raw image, and then also at the first threshold, and also at the standard deviation. As you can see, at the first standard deviation, there is a lot of, at the mean, there is a lot of noise in the image. You're not able to clearly make out where the actual oil is. At the first standard deviation, though, you can clearly see where this oil slick actually is. It's clearly illuminated. Therefore, I decided to use this first standard deviation as my best guess on the actual size of the oil slick region. I also applied this idea to the second and third standard deviations while doing an ROI overlap of all three of these, showing almost a density image of the oil slick. As you can see, in the second and third standard deviations, you have more of a clear picture of where the more dense oil is, which tends to be more or less in the middle of the oil slick. Now, this is great, but can I apply the same methodology to the upper and lower regions? First, the upper region, which was a little bit more problematic because it was closer to the side of the flight track, which means that cross-track illumination problem comes into play. Also, the lower oil slick region shown respectively with its ROI. Now, as you can see, that cross-track illumination problem manifests itself in that mean on the upper oil slick region, in that right side of the image is a lot brighter than it probably should be. Nevertheless, the first standard deviation on both values represent a pretty clear approximation of actual oil slick sides with their respective higher density areas. Now, putting this into a chart, I get this. Now, let me break down this chart real quick for you. If you look at the first standard deviation along the combined area, we get a value of 3.741 kilometers squared, which represents my best guess on the actual oil slick size in the Santa Barbara Channel. Now, also here we have the different density areas, ranging from low, medium, and high, along with the actual noise factor, which was that stuff that just triggered at the mean. So thus, this gives me a way to be able to quantify the different densities along with the total area of the oil slick. Nevertheless, now that I've shown that I can quantify the area of the oil slick, can I also predict where these oil slicks are going to move to and what factors play into this? In order to do this, I first turn to this image, which is a sea surface current image of the Santa Barbara Channel. This image was obtained from Dr. Washburn of the UCSB Ocean Surface Currents Mapping Project. Now, as you can see, each of these black vectors represent the different sea surface current directions and magnitudes. Now, this image is actually during the 3 hours with 2.5 hours before and then the 30 minutes during our flight. Thus represents a pretty clear picture of the actual oil slick, like where it's going to be going during that time interval. Zooming in on the region of interest, we see the gray box, which is actually Platform Holly, along with the Isla Vista and UCSB. Now, I go in back to the master image and then superimpose the sea surface current imagery onto this, as seen here. Now, as you can see, the oil slick is traveling about this direction. It's traveling east to west, but with a slight north tick to it. Thus, I had to ask myself, what accounts for this north tick? If it's not sea surface current, what else is playing into? I looked first to a Santa Barbara buoy, which actually recorded wind direction data, which gave me about this direction, though it varied between here and here. If you combine these two vectors, and then you see that gives a pretty good image on where the oil is going to go. It predicts it reasonably well, with the wind direction adding that slight upward tick that is not noticed with this surface current. You can also see that La Seeps are highly active right here, spewing out immense amounts of oil. Applying the same methodology to the upper oil region as well, you can see here Shane and Ira Seep along with Platform Holly. Now, superimposing once again the surface currents onto the image yields this. Now, you can't really make it out from the back, but you can't really make it out from the back, but these black arrows represent those oil slicks that seem to be stemming from Shane and Ira's seep. As you can notice, once again, if you apply wind direction along with surface current, it gives a pretty good estimate on where those oil slicks are going to head to. Granted, though, the very top one on the Shane seep, it seems to be curling up a little bit more than expected, especially considering that the sea surface current starts to change right about at that level. Now, let's zoom in also to platform Holly. Take a closer look at that. There are two main oil slicks surrounding platform Holly. First, we have one on the left, as well as one on the right. Looking first to one on the left, barely visible, though highlighted by this box, it seems to be flowing pretty clearly east to west. Once again following the sea surface current direction and magnitude. But then we have an oil slick to the right of platform Holly. Now, judging by the diffusion pattern, it seems to be heading southeast, which is unexpected, considering that this goes against both the wind direction and the sea surface current information. Therefore, I have to ask myself, is it actually flowing this way? Perhaps instead it's actually flowing with the sea surface current this direction. But this doesn't quite make sense, because one, it doesn't fit the diffusion pattern, and also it would imply that there is potentially a new oil seep location. Now, this is a distinct possibility, but it is taking a large leap of faith in considering that there actually is an oil seep location here. Also worthy to note on this image is that platform Holly is clearly leaking oil. Moving to conclusions. First, I have shown that the master thermal image, along with the MODIS sea surface images, overlap pretty well, showing a high level of correlation. I've also been able to effectively locate oil slicks in the Santa Barbara Channel, as well as quantify the area of those oil slicks using the visible spectrum. I've also been able to predict the future locations of oil slicks using a combination of sea surface current along with wind direction data. But is there really more to this picture than meets the eyes? Well, being able to quantify the area of the oil slick, along with predict where it goes, is that really the whole purpose of this? Is that really the point? Or is the point really what we learned? Such as the problem-solving skills on dealing with an image that, for inexplicable reasons, appears to be a bright lavender color after a cross-track illumination correction. Or perhaps dealing with the frustration of trying to mosaic two master images together that just do not want to be mosaic together. Granted, creating my own research project has its own hardships along the road. But as with any research project, as with any research opportunity, any worthwhile research opportunity, the reward comes from that tedious and tiresome and frustration that you get out of it. But persevering through that allows you to call something your own and be able to call it, it's mine. I did this. And I have to thank these people for having that experience, specifically Sherry for dealing with my constant pestering and constant questions, along with Dr. Kudela for guiding me in the right direction, along with Shane for endless envy help, Dr. Washburn for the sea surface current image, Amelia Snow for the sea surface temperature image, along with the different people at the Dryden Research Center, along with, of course, Emily, Rick, the SART program, NASA, and NSERC. Thank you.